Autumn is the XML specialist at Design Science, where she works with publishers, engineers, and educators and programmers to include MathML and XML publishing workflows. Autumn developed CellML, an XML language for describing biological models and associated metadata and ontologies. Robert Miner leads Design Science's research and development effort. He's led the development of the Design Science product line from its inception and now oversees development of the DSI product line. He's helped initiate research programs for adding value to electronic math content, particularly in the areas of math-aware searching and mathematics accessibility. Robert co-chairs the W3C Math Working Group that developed and maintained MathML, and we're very delighted to have you both. If there's anything you want to know about math and publishing, Autumn and Robert can tell you. Now I'll turn the presentation over to Robert Miner. Robert, it's all yours.
Good morning, everyone. Thanks, Liz. I hope you're all comfortably settled in. And Autumn and I hope all of our cups of coffee are eager to get into it and tell you some interesting and engaging things about math and technical publishing this morning. Let me begin by sort of outlining what we'll be talking about today. So I want to take a somewhat broad view of the subject matter, given that it's somewhat specialized, and so we need to establish some context. I want to start by looking at where we are today with technical publishing and how that works. Then I want to look at some recent developments, especially over the last couple of years, that are just coming to fruition now. We're getting a very nice convergence in tools, standards, and technology that poises us for some exciting developments, I think. And so we want to spend some time today looking at those developments. And then we're going to shift to what that might imply for the future. Where we are today is basically XML-centric workflows and tool chains. That's the dominant model. That's taken about a decade or so, I think, to really settle in, but most major publishing workflows of any scale that I'm aware of are largely XML-based today. Design Science and Arbortext PTC have been partnering for many years to support technical publishing in XML workflows. And so in this first segment, what we want to look at is how Arbortext and MathFlow software work together to support a traditional XML publishing workflow for technical content. And by that, what I'm really focusing on is math notation. There are, of course, other aspects to technical publication, graphs, charts, diagrams, but our business is really the math portion of that. Then we'll move on and we'll look at this convergence, and that, to some very large extent, I think, can fall under the category of HTML5. MathML is a specification for encoding mathematics in XML. It's been around for a long time. So is HTML, but the two have never played very well together. And finally, with HTML5, which is, of course, creating quite a stir these days, math will actually be a first-class citizen there. And that's had a lot of spillover effects that has stimulated adoption in other standards and technology as well. DAISY is an accessibility standard, EPUB is a eBook standard, and so on, and MathML is now making more of an appearance in those contexts as well. And we've seen the same thing in software, browsers, Microsoft Office, ink input, assistive technology, a whole range of things are finally sort of all reaching the same level of maturity so you can connect them up, and we want to look at that convergence. And we think, at any rate, that generational shift in technology is going to piggyback on top of broader trends in web publication and communication in society in general, and have some fairly profound effects in the next decade of technical publishing. Many observers have noticed a shift from desktops to browsers and devices and tablets, and that, of course, will have very major implications for how we consume and share information of all kinds. that implies a shift to web applications as a dominant mode of software delivery. And we think that is going to make easy reuse and interoperability of content on small screens and big screens and everywhere an essential operation. So we want to look a bit at how that works for math data. And then we'll speculate a little bit about what new collaboration models and new ways of organizing ourselves to do science and technology might emerge. So that's basically what we're going to be doing today. So let's start in, where are we today? Well, XML workflows. So as I was just arguing, I think the dominant model for STEM publishing, that's the whole range of technical subjects, science, technical engineering, medical content, most of that's based around XML. Now, it's not particularly new that publication follows a particular workflow. There are a certain sequence of logical steps, but they have sort of a characteristic appearance within an XML workflow. And I'm sure from your own day jobs, you're all familiar with how this goes in your own context. The main steps go something like this. There's an authoring phase where authors create documents. And by and large, it's unusual still because authoring is a very optimized, idiosyncratic, specialized, domain-specific thing. We tend to use non-XML tools for that still. And I think that's probably not really subject for change. People use Word, people use web-based authoring systems, people use old languages like LaTeX, a whole variety of particular tools. But what has changed is those tools, even if they hide the XML pretty deeply now, are all expecting to export or convert their data to XML in some fashion. And so after that content is created, we bring that data into a workflow via some sort of conversion or export operation. Generally, if it's an operation of any scale, that data goes into some sort of content management system. And the result is what, at the World Wide Web Consortium anyway, we tend to think of as a compound document. There's a document level language like DocBook or DITA or any of a number of others. And then within that are mixed regions of data in other XML vocabularies, equations encoded as MathML, and so on, graphics as SVG, what have you. Math is almost universally encoded as MathML and XML. There are a few alternatives. Some people keep legacy data around in an XML wrapper. But as far as true XML encodings of math notation, MathML is really the only game in town. It's quite mature now, and that's, I think, established. Once you have that data, it goes through some editing and production workflow, and there is where we all live. That is done with tools like Arbortext, augmented by products such as the one we make, MathFlow, for editing the embedded math content, and perhaps other helper tools for other embedded content types as well. And of course, the whole raison d'etre of XML is that once we have that final document approved, then we can compose it out to a whole variety of media targets, and people certainly do. PDF, HTML, Word documents, help sets, the whole range. And at least in the context that all of us spend a lot of time, we do that with tools like Arbortext Advanced Print Publisher or Publishing Engine, often augmented by processes using XSL or other style technologies and whatnot to assist us in doing the plumbing. Now, that's what the process looks like in the large. What I'd like to do now is hand things over to Autumn to show a bit how this works with our own product, MathFlow and Arbortext, working together. Autumn?
Okay, so a lot of content authors still prefer to use Microsoft Office. It's very easy to use, and a lot of people are comfortable with it. So this is a sample Word document, and it has several equations in it. These equations are MathType equations. Bring that over here. And MathType is Design Science's flagship product. It works with hundreds of applications. Most STEM publishers or STEM content authors are familiar with it. It's been around 20-some odd years. One of the applications it works with is the Math Input Panel, which is new in Windows 7 for accepting handwritten math into your computer. And if time permits, we'll demonstrate that a little bit. But obviously, it also works with Microsoft Word. So Arbortext has this handy little tool for importing your Word documents. But typically, well, naturally what happens is these MathType objects are going to be converted as images once Arbortext imports them. So Arbortext is creating your XML document, but it leaves the equations as images, and that's just not very useful because if you have to make any edits to the equation whatsoever, like change the style to your publication style, it's you'd have to go back to MathType, re-edit it, and then re-import that equation. So you really want to bring that in as MathML so that you can, apply your XML styles to the MathML as well. So MathFlow works with Arbortext's import process. It's behind the scenes. You pretty much don't see it. Because of time, for the sake of time, I'm not going to show the import process today, but if you are interested in seeing that, then please contact me afterwards. But what you wind up with is this is the same document. It's been imported into Arbortext, and you'll see that these equations are all MathML. If you look at your document map, when you click on the equation, it updates in the document map with the MathML. What MathFlow does is it creates preview images of each of these equations, and you can double-click on the equation to bring it up in the MathFlow editor, and you'll see it's a lot like MathType. You can make a change to the equation, and once you click OK, this preview image is updated. What's saved to the XML document is just the MathML. The preview image gets deleted at the end of your session. But with the preview images, you're allowed to see what exactly the MathML is showing you. You can also edit the MathML directly. And while the preview image doesn't update automatically, you have an option in MathFlow to update the preview image. So MathFlow also works with Arbortext's compose features to compose various outputs, including HTML and PDF, and it also works with Arbortext publishing engine for the same purpose. So for now, I'm going to compose to HTML. You'll see that MathFlow adds this new section to Arbortext HTML composition and for treatment of the equations. You have two options. You can convert those MathML equations to images. This is the old-fashioned way of doing things before there was cross-browser support of MathML. But right now, we're going to just leave those MathML equations, and we're going to choose a script that's been modified to produce MathJax output. And I'll describe MathJax in just a second. So we're going to create an HTML document. And while that's generating in the background, it's already been produced, I'll describe for a second what MathJax is. MathJax is a joint effort led by Design Science in conjunction with the American Mathematical Society and the Society for Industrial and Applied Mathematics. It's an open source JavaScript rendering engine to read in the MathML and the tech in your web pages. This makes it so that you can open your document in any browser, and even browsers that don't natively support MathML, such as Safari at this time, will be able to open the document and show all of the equations beautifully rendered, and you'll see all your changes are in there. The that's just an example of how MathFlow works with your XML workflow. I'm going to pass this back over to Robert.
Thanks, Autumn. So, as you see, what Autumn demonstrated was basically all those steps in the traditional XML workflow: the authoring, the import, the copy editing, and the composition. But even from that brief demo, it is clear that such a workflow doesn't exist in a vacuum. There's a whole sort of ecosystem that surrounds it, and this is because both the producers and the consumers of STEM content do a lot more than just read printed documents. They interact with a whole variety of tools and communication technologies all around the periphery of that workflow. On this slide, what I've done is I've listed out design science products that touch on this workflow. But, of course, there are many other pieces of software from other companies that also touch up against the workflow and create a whole ecosystem of interacting applications. So recall we started out with MathType, and MathType was here used in this traditional authoring role, creating a Word document. But Autumn mentioned this. MathType certainly cuts and pastes between other applications as well. And we'll say a lot more about that today. MathType's kind of this bridge. It was the math authoring tool that plugged into Word, but it touches up on other things, and hence the ecosystem expands. A product we didn't look at, one of those products that touches up against MathType is something that we call MathDaisy. Our interest in our role as XML publishers was getting that content from Word into our XML workflow. But if you're a high school teacher and you have a kid with visual disabilities, then your interest might very well be producing some accessible version of that Word document. And MathDaisy is a tool that we have that interacts with MathType and some other software to produce something called a digital talking book, something that implements that DAISY standard that I mentioned earlier, that could be read by a screen reader for that kid with visual disabilities. Now, on the other end, we obviously, when we got something out of the workflow, we composed it to HTML with the view of publishing it on the web. And there, what Autumn showed was MathJax. And we'll be seeing a lot more of that. That's a display technology for MathML and browsers. But with HTML5, as I was talking about, there's also a lot of interest in native implementation in browsers, alternative implementations in browsers. One of those tools that Design Science makes is called MathPlayer. It's been around a long time. It works with Internet Explorer to display math. But here again, we see this sort of ecosystem aspect that MathPlayer also bridges to a number of other pieces of software. In particular, it's a display engine for screen readers, and its main thing is providing accessibility. It would be used by the reader that MathDaisy was targeting when it produced that accessible content. And so you get all these interconnections, arrows coming in and out of your workflow at various points. And that is what we want to turn our attention to now. I tend to think of it in over-melodramatic terms, partly because I've been working on this for many, many years, as the grand convergence. I think that there's a sort of gelling taking place between a number of areas of that larger ecosystem that have been a long time in the works, that are going to really start making a difference in people's lives. And so that's what I want to talk about now. So let's try to put a little finer point on that. Well, so when at the beginning of the web explosion in the early and mid-90s, there was a lot of thinking about electronic communication, and the people in STEM areas sort of began working out a vision of high functionality scientific communication. And the genesis of it was basically this. When you think about mathematics as opposed to text, one has the sense that it's more rigorous and precise in some way than natural language. And we ought to be able to get some mileage out of that. Now, if you think hard about it, it's not quite as precise as you'd want it to be. It's not like a computer language, and it's not like symbolic logic. People abuse notations and leave things out and whatnot, but still it feels more controlled and more tractable. And what the general sense is, and I think this is sort of felt by many users of mathematics without articulating it, is that a formula should not only represent something visual, how a notation should look, it should also basically encode what the mathematic means sufficiently well anyway for mechanized agents to do good things, help us communicate more easily in some hard to specify fashion. Well, so when people began looking at XML technologies for scientific publishing, they tried to come up with a statement of what that ought to mean. And it's a relatively short list. Basically, you need math to display at high quality and adapted to the media it's in. That's essentially print and media, and electronic media, though those are quite different. In electronic media, you have all the issues of line wrapping and whatnot, resolution. You need it to be authorable in a variety of ways. Now, for text, this is not really such a question. At least until recently, the keyboard was the way you authored text. But with math, it's not nearly so obvious. How a sixth grader taking a standardized test might need to make a math notation could be quite different than how a technical publisher wants to. The two-dimensional aspects of math authoring mean that the best way to go about it really kind of shifts with who's doing it and what purpose they're doing it for, which is something you don't have to wrestle with in text. At the same time, because math should mean something, it seems like one should be able to search on that meaning and make that meaning accessible by reading the equation intelligibly, not merely as a jumble of symbols, but as a mathematical statement. And similarly, and this is the one that is really the payoff, you feel like math gets used in this whole range of applications, from display and authoring and editing, but also in symbolic calculation, in learning software, in all kinds of scientific applications. And one sort of would like to arrange for simple cut and paste of a formula to do the right thing in the right context. Well, okay, so this was the expansive vision. Gosh, with XML, we ought to be able to encode all this information and make all these good things happen. Well, it turns out that, each one of these bullet points, as I was suggesting, is actually really hard, much harder than for text in a lot of ways. Line wrapping words, not so hard. Line wrapping a complicated fraction, really hard. Authoring text, simple keyboard interface. Creating a complicated equation, not so clear anymore, and so on down the line. Well, so when the MathML project started at W3C, these all got enumerated as goals. And by setting them down as a manifesto, this has kind of made it a focal point for this whole program, and it's kind of been in the center ever since. So if the convergence that I'm talking about, I think, has to do with that program finally being, at least in its basic outlines, finally realized. People didn't, I don't think we anticipate, I certainly didn't anticipate how hard and long a project that was going to be at the outset. But finally, I think the end is sort of pulling into view. And so what today is we're going to do with the rest of the time is we're going to show various ways in which I think we can argue that that program is now being completed. MathML is unusual as an internet technology in that this story is played out over nearly 15 years, which is forever in internet time. But technical publishing is a dependable 5% that of all content. It's not very sexy or glamorous, but it's always there, and it's been persistently there. And so gradually, math has worked its way up the priority list. And if it wasn't in version 1, Sometimes it is now in version 2, 3, 4, or 5. And so this is where the convergence comes in. I spoke about how MathML is part of HTML5. It is part of this accessibility standard. It's being discussed for addition in the eBook standard. It's part of a PDF accessibility standard and so on. And these have all been lengthy processes. As you see, these all have higher numbers, but finally math has arrived there. And the same thing has occurred with software systems. It's taken a while for it to work its way up the priority list, but now one has MathML support directly in a number of Microsoft Office apps. Autumn mentioned this pen input component that's been added to Windows, and it speaks MathML. MathML has been added to the Mozilla codebase for a long time. It's now being added to the WebKit codebase. It's over time been implemented by a lot of computational software and a lot of learning management software. It's in accessibility software. And so slowly over time we've had a gradual accretion of MathML support. And so what I contend is many of these pieces have now finally gotten to the point where you can connect them up. The whole program is finally gelling, and I think this is quite exciting. All right, well, so enough background. What's actually in MathML 3, this latest version, and what's in MathML in general, because I assume some of you at least are only partly familiar with it. Well, so MathML has basically, in the first version of MathML, it laid out this basic architecture of an XML encoding of math. It had a vocabulary for describing how equations looked and a vocabulary for describing how equations mean. And we worked closely with the Unicode technical committee to start rationalizing fairly incoherent and sporadic character support for mathematics. That presentational vocabulary tries to respect mathematical structure. It encodes things like superscripts and fractions and tables and underscripts and overscripts, but it does it in a way that identifies the various pieces. So it's this superscript attached to this base expression and so on. This is standard XML design principles, but it's very useful for math, and it's a very natural method. Well, in spite of this being a good thing to do, and a very early initiative, MathML was one of the very first XML vocabularies to be standardized. It actually came out as a W3C recommendation the year before XML itself was finalized. And to some extent, it was before its time, and the version of HTML in development at that time was 3.2, and we tried to get it in there, but it didn't make the cut. Well, so then in 2003, I think it was, there was now a fair amount of practical experience, and the rest of web technology had really kind of caught up a bit and was definitely focused on XML. Things like CSS were being developed, XSL was being developed. So there was a second version of MathML that put a lot of effort into properly integrating with those technologies. Reworked some functionality, filled in some gaps, did a lot more work with Unicode, adding characters. Didn't help, still didn't make the cut in HTML4. So in the intervening 5 or 6 years, a whole lot of what we did was at W3C leaning on getting math into HTML5, by golly, and this time we succeeded. The other things that MathML 3 kind of does is round out its own program. It's always been intended to be an international standard, and one surprising thing that we discovered over time was that there was really quite a lot of interest coming out of Arabic-speaking countries for right-to-left mathematics. And so MathML adds a lot of bidirectional support, something you don't think a lot about in the US these days, but it's important globally. We've talked a bit about accessibility. We did a lot more for accessibility. We'll see some of these things. And then coming out of the technical publishing, professional publishing community, a sore spot has always been control of line breaking in large expressions. And so MathML 3 finally rounded out some functionality there. It also did some things for the computer scientists in providing a sound logical basis in terms of mathematical logic for defining the meanings of expressions. Not quite so so strong in its practical implications. So, just because we can, I'm going to hand it over to Autumn again here in a second. Let me show you a page, though. So the significant thing for MathFlow and Arbortext is that MathFlow will be implementing MathML 3 in the next version. To get a standard to advance a standard to a recommendation status of W3C, you have to show a certain level of implementation as judged by a test suite. And so the rendering engine from MathPlayer, which is shared with the Windows native components in MathFlow, that was really the reference implementation for MathML 3, as you see by this column here. Every feature has to have 2 compliant implementations. And so MathPlayer pretty much attempted to pass the whole test suite. These numbers aren't all 100% because not all of these tests were required. Some of them are tests that are intentionally not, or error handling tests and stuff like that. But now the column labeled MathFlow here doesn't look so good, but that is really something of an artifact. That was the JavaScript rendering engine, the Java rendering engine from MathFlow. And while we're implementing MathML 3 here as well, the implementation lags behind. We did the C++ engine first. And so for this test, all we did was we kind of cherry-picked tests where we absolutely had to have a second implementation, and we implemented those in MathFlow. And that's all that is represented in this table. So now let me hand that over to Autumn, and she can show you that development copy of MathPlayer showing off some MathML 3 specific features.
Okay, I'm going to start with line breaking, which is probably the most important to this audience. And I'll be showing this using MathPlayer 3, which is in alpha right now. It's not quite ready for release, but it definitely has implemented, as Robert was just showing, it's implemented most of the MathML 3 features. So this is an example of the new line breaking in MathML 3, and here's some of the code behind it. What you have here is here's the first equal sign, and this one is the second equal sign. So you have the line break specified as new line, and the style is specified as before the equals. So we're going to break the line before the equals. And you're going to align this next line by the ID that's equal to EQ1-equals. So we're aligning it against the first equals sign. Previously, in MathML 2, would have had to have been done by tables, which is slightly less elegant. MathML 3 also includes some features for automatic line breaking and specifying indentation so that it lines up a little bit more with what you would get from formatting engines such as XPP. The second one is the BIDI support. You can specify a dir attribute on the math element, and by default that's LTR for left to right, but once you switch that direction, here we're switching it to right to left. This is MathPlayer showing it in right to left, which looks a little bit trippy to the Western audiences. I'll also show for a second MathPlayer's new accessibility features for elementary math. Right here we have a stacked addition problem and a long division problem. And MathPlayer has a speak expression feature that allows you to speak the expression, and MathPlayer will read out the MathML for you. And this is all possible because MathML 3 has the correct encoding now.
Addition problem. 424 plus 33 equals. End of problem. Long division problem. 1306 divided by 3 equals 435.3. Here's why. 3 times 4 in the hundreds column equals 12 in the hundreds column. 1306 in the ones column minus 12 in the hundreds column equals 1 in the hundreds column. Next step. 3 times 3 in the tens column equals 9 in the tens column. 10 in the tens column minus 9 in the tens column equals 1 in the tens column. Next step. 3 times 5 in the ones column equals 15. 16 in the ones column minus 15 in the ones column equals 1.0 in the ones column. Next step. 3 times 3 in the tenths column equals 9 in the tenths column. 1.0 in the ones column minus 9 in the tenths column equals 1 in the tenths column.
So that's a few of the exciting features for MathML 3. This is pretty exciting for the accessibility community, and I'm going to hand this back over to Robert.
Just to emphasize, that was not alt text that was prepared by a human being. That was purely algorithmic reading, just looking at the structure of that XML markup. And that's leads into our next point. An area where we've seen really strong convergence in functionality is in accessibility. Accessibility has always been a challenge for STEM content because it's hard, it's two-dimensional, it's just inherently difficult, and people with visual disabilities are traditionally way underrepresented in STEM professions. And so when MathML attempted to represent meaning and structure so carefully, that was embraced by the accessibility community in a big way, and it's been a catalyst for a lot of work on math accessibility over the past decade or so. And that shows up. MathML has been embraced by a number of standards and regulations. It's in this DAISY language for talking books. The third revision of the standard just delegates out to MathML. That's significant in the U.S. because DAISY actually has some regulatory force. There's a national standard for K-12 textbooks called NIMUS that largely references parts of DAISY, and that moves forward with a slow rules-making process, and so it doesn't yet reference DAISY 3. But when it does, that will essentially mean MathML is required for textbook publishing for accessibility. And similarly, MathML is in the being standardized as a way of tagging in the backplane PDF documents for accessibility, and there are discussions now under the EPUB rubric of exposing MathML for accessibility. Now, of course, there's a big gap between standards and the real world, but I think accessibility is one of the exciting areas because it's actually making a real difference. Our senior scientist, Neil Seufer, has done really commendable work, NSF-funded work in this area to advance math accessibility, largely using that MathPlayer accessibility engine. There was a major study called Project SMART in Kentucky about a year ago, trying to document some of this, and it basically found a strong correlation that the more MathML was used in course materials for students with visual problems, the better their scores were, the more they enjoyed the class, and the more independent they felt. And that's a very significant result. Most major screen readers and other voicing learning tools, a lot of kids with dyslexia and whatnot, with not actual visual trouble, benefit from synchronized highlighting and voicing, as we saw. Most of those now support MathML, a lot of them by calling out to that MathPlayer accessibility engine. Sort of a striking statistic is in the last couple of years, over 4 million expressions have been spoken aloud by MathPlayer. So it's not like it's just sitting there, it's really being used. And then otherwise, design science has been fairly active, as I mentioned before, developing authoring tools to empower educators, mostly starting with Word, not going going directly through XML workflows, both with Braille vendors to refreshable Braille displays for math, and then also to produce DAISY books directly. Just because I think this is such an exciting area, I'm going to hand it back to Autumn, and she's going to now show off a book that had been prepared in that way.
So this is a DAISY digital talking book that was produced with Word and MathDAISY. And it's going to be read by GH Player, which is a screen reader, and it uses Math Player to speak the math expressions, and the math is encoded as MathML.
By Bob Matthews. Powers and exponents. There are some simple formulae that you can use to manipulate expressions containing exponents. Some examples are mathematical expression. X super n, y super n equals open x, y, close super n. And of mathematics book pause.
And I could probably keep watching that. I find it completely fascinating, but I'm going to hand this back over to Robert now.
Simple math.
The significant thing there is the integration between the math and the text. That's the kind of convergence that we're looking for. That screen reader just read seamlessly through the words into the equation. And a student who needed to understand that could back up and go forward and back and forth across the text and the math to build up that mental picture that's vital to understanding. And so that's why this is so significant. That kind of integration just wasn't present before. The way, just as a research aside, one of the things that we're working on a lot now is trying to come up with better ways to allow blind and visually disabled people to navigate within a math expression. That's not so obvious because it's not just forward and back like it is in text. You kind of want to be able to move around in that two-dimensional structure, but it's really the logical two-dimensional structure. If you're trying to understand a fraction, you don't necessarily want to back up the words. You want to be able to say, what was the numerator again? What was the denominator again? And move around in sort of those logical directions. And so that's an area of active research. That's kind of a difficult problem. At any rate, so we have convergence at the level of accessibility. What about browsers? Well, so I'd like to compare and contrast browsers and accessibility because we were just so wrong in the early days when we were beginning to work on MathML at the World Wide Web Consortium. World Wide Web Consortium had made a special emphasis on accessibility, thinking this was something that the web could really offer the world. And so we dutifully put a lot of work items in our charters about doing accessibility, and all signed on to that expansive vision. But we all assumed that what it was really about was doing math in HTML pages, and that was where our real interest would lie. So here we are 15 years later, and you have all this wonderful software out there deployed, making a difference in students' life for accessibility. And the thing you still can't do very easily is display math in web browsers. So it just goes to show. But that situation is getting better too, and HTML5 is very strongly influencing that situation. So what's the issue with web browsers? Well, forever you could always expose math in web browsers as images, and that's typically what people have done, or they've just published in PDF and kind of gone outside the web paradigm. Well, so for math to really work right, you need a bunch of things images can't do. You want it to match the surrounding rendering. If you want it to print well. A key one for things like accessibility and interoperability is it needs to expose data, and that's hard to do with images. And of course, you need to have acceptable speed and quality and require nothing of the reader. And that was always a big appeal of images because it required nothing of the reader. it kind of stumbled on all the others, but it was this one that was really the driving factor. Well, so to get those other ones, you kind of need to get data into the web page. And so people have been working on native support for a long time. Mozilla had it. Right after it went open source, people added it to Mozilla. And we built MathPlayer to work with IE, and that works quite seamlessly and nicely. But it didn't really solve the problem because those two browsers were fundamentally incompatible. Mozilla would only display XML documents with MathML, and IE would only display HTML documents with MathML, and so that required sophisticated content negotiation. And even if you worked that out, there was no solution for other browsers. And so we've kind of been trapped there for a long time. Well, so this is all settled in HTML5, and that's why it's so significant. Now MathML is really in HTML, and the markup incompatibilities between IE and Mozilla are about to disappear because it's part of the standard. And that's prompting a whole bunch of additional native implementation. WebKit, which is Chrome and Safari, are in the middle of implementing. It's in the nightly builds already. And even Opera has already deployed partial support for MathML. And that's significant, of course, because Opera, though not big on the desktop, is much more important on devices. So we're seeing a whole lot of progress, finally, in the area of standardized native implementation in browsers. But for real-world publishers, I think that this problem is just the same. What about the rest? If you don't have those newest browsers, what do you do? Well, so this is why MathJax, which Autumn showed off earlier, is so significant. All this time while people have been struggling with native implementation, what's happened is the rest of the web technology has gone really good. And so some years ago, we noticed that the capabilities of JavaScript, CSS, and web fonts were actually sufficient to do really wicked math rendering in a browser. And that is supported in browsers today and actually a generation or two back. And so what MathJax does is it basically looks at the browser and chooses how to display the math and gracefully falls back depending on the functionality in the browser. And so that's really significant if you're a publisher because it means you can rely on the native rendering and the highest functionality and the best performance and the nicest font management and so on and so forth if the user has a browser that can do it out of the box. And you have a perfectly good, high-quality fallback otherwise. So that means that people can now really begin to publish web documents with that MathML data exposed in them for all this high functionality and not really compromise on any of the desiderata for effective web publication. So we're really excited about this project. Version 1 just came out in August, but I highly suggest that you take a look at that, www.mathjax.org. Now, to me, the browser problem is still there, but getting better. The significant thing about it has to do with these broader trends toward exposing data for reuse, exposing it for accessibility. And so what I want to do now is go over to Autumn and show off how that kind of works. If we can get that MathML data into our publications, we can start to do really good things with it. And this is probably the real punchline to the convergence argument.
Okay, so what I'm showing is interoperability between the browser and other applications, and this is on mathjax.org. It's done through MathJax. MathJax adds these context menus to the equations. If you right-click on them, you have the option to show the source and to change the format of that source depending on how it's configured. You have options for producing that source as MathML or TeX. So in this example, we're going to change the format to MathML, and we'll use that as the format that we want to copy into other applications. You can show source for this equation and select the entire equation, Control-C or right-click to copy it. And then you can paste that MathML block into another application. This is Mathematica, and Mathematica recognizes MathML. So you see here that it's asking you if you want to paste the typeset version of the expression. Once you click yes, you get the beautifully typeset MathML equation. The same equation is on the clipboard. We're pasting it into Microsoft Word. So if you, naturally it escapes all of the XML, but you can keep it as text only, choose the paste option, and it will display the typeset version. So most applications that accept MathML will accept the version from MathJax. Most will either look for the MathML math element, or they'll look for the namespace declaration, which are both provided by MathJax. Now we'll do the same thing for the same equation with using TeX as a format. Once we show the source, we can copy the equation to the clipboard, and we can paste that into any application that recognizes TeX as a format. One of those is MathType. So for any of you who prefer to write your equations as TeX or LaTeX, you can insert that into MathType. Wikipedia also accepts TeX. This is the Wikipedia sandbox. It's for testing purposes. And once you paste this in, you do have to delimit the equation with a math element that will tell Wikipedia that it needs to treat the string enclosed in the math tags as something special, and it will render that equation in the web page. Just a quick tip, you can also, if you already have the equation in MathType, MathType will allow you to copy that as with the Wikipedia delimiters in it with a MathML element if you set your copy and paste preferences. I would show that, but I think we're running out of time, so I'm going to hand this back over to Robert.
So I think that's fairly impressive. We could go on that way for a long time. Maybe if people have some interest, Autumn can show the second demo showing MathType interacting with a bunch of other applications. But a significant thing there is that by and large, all of that cut and paste interoperability just arose organically from all these individual applications and websites exposing their data in standard formats. Nothing had to be done specifically for that demo, and that's why we could go on with that demo for a long time, cutting here, pasting there, cutting here, pasting there. Well, so we're coming to the end here. So I've been arguing that we've had this convergence. So where do we go now? At the beginning we noted that there were some larger trends at work here too, and the combination of the STEM technology convergence and those larger trends was going to have implications for technical publishing. So one area that I think is already pretty clear is going to happen is we're seeing a shift in emphasis from desktop apps to browsers, devices, and tablets. We've talked during the presentation about how that is going to have some implications for how we edit and the editing models and perhaps even display. One practical consequence that we're looking at hard at Design Science is using Arbortext and MathFlow as a publishing platform for an ebook workflow. As you saw, there's work on putting MathML in the backplane in eBooks. There's also an issue with converting MathML to SVG graphics with appropriate cross-references to the MathML for eBooks. So that's an area of interest. It's clear that as we move to devices, and web browsers, what that's going to mean is web applications, cloud applications will become increasingly important for display and authoring. We've already started seeing that happen. We make MathFlow components available. I guess perhaps I'll shift back over to Autumn and she can maybe do this in parallel while I talk over this last slide. She can show an example of using MathFlow components to do a web-based authoring platform. And this is also a direction that we think maybe there will be interest in pursuing within the MathJax project, a purely client-side JavaScript-based math editor. There are several out there now that are not very sophisticated, but seems like the possibility is definitely there. Now, another shift that really ties into that interoperability piece is that I would say that if you take the first 2 points together, oh, Autumn, you're giving it back to me?
Oh, yeah, sure.
Okay. So if you take those first 2 points together, what you conclude is that there's a transition taking place from users gaining a lot of deep knowledge about a few big applications, which has been the way computer use has tended to run in the past, where you become an expert at using Microsoft Office, or such as most of us are, experts at using Arbortext and MathFlow tools or whatever, and we live within those product suites. And moving to a usage model where you have lots of applications with relatively simple interfaces and shallow knowledge. We all know this too from the little bit of interaction we do on our banking website and the movie ticket renewal reservation website and so on and so forth. And so certainly the first category won't go away, but the second one will become increasingly important. And I think what that means is that that kind of cut and paste interoperability to allow easy reuse in different contexts of all kinds of information is going to be at a premium going forward. And this is an area that we see as particularly important for MathType, where we have this very sophisticated detection and transformation engine. If we'd had a little more time, we could have seen copying back out of Wikipedia and pasting into other applications. MathType can recognize Wikipedia pages, figure out how to extract the math data, convert it back into MathML, and repurpose it that way. The converse of that is that as publishers, exposing that data is going to have more and more value. It'll have value for accessibility, it will have value for interoperability and reuse, and it'll have value for discovery and search. And that really is where my crystal ball kind of gives out. It's clear that this is the new frontier. Within the research mathematics community, there are a couple of projects that are worth noting that are making a huge stir. One's called mathoverflow.net. The other one is called the Polymath Project. And these are new experiments in social collaboration in doing science. Traditionally, one does math problems standing at a blackboard or with pencil and paper, and a guy thinks really hard about it and comes up with something. Over the years, the American Mathematical Society has tracked this, and we've seen a steady but very slow increase from almost all papers having one author to now 2 or maybe 3 as people have begun collaborating more through email and whatnot. But MathOverflow.net and the Polymath project take a completely different approach. Someone poses a research topic, and a large communal group of people work on it, post bits and pieces, share the results, break into little groups, and they have been proving theorems that can't quite be attributed to even a well-defined set of individuals, but it's clear it's quite productive and stimulating. And so coming to terms with what that means for how science is conducted is really quite thought-provoking. It's clear that discoverability will be at a premium, and reuse and repurposing will be at a premium. Math search is an area that I myself have worked in a little bit and would like to do much, much more with as the volume of exposed MathML data becomes greater in the world. But where does that lead us? I don't know. Will we all be tweeting equations to each other soon? It seems possible anyway. At any rate, that's, as I say, where the crystal ball leaves off. So if you have thoughts or questions about that, perhaps we can go into them afterwards. Let me just summarize our conclusions. So today what we've done is we've looked at progression. Today, where technical publishing is XML workflows supported by tool chains like Arbortext and MathFlow, taking documents in from a variety of sources, getting them into XML, and then targeting them out at a variety of media. What's been going on over the last few years is we've had a convergence of STEM communication technologies centered around MathML, being driven by HTML5, accessibility, interop, browser display, and many good things are coming together right now. And so what that's going to lead to is a strong push toward interoperable web apps deployed via browsers and devices. And if I am lucky enough to give another one of these seminars in 10 years, what I suspect we'll be talking about is all the innovative new ways that we've learned to harness that new STEM communication ecosystem to organize and collaborate in different and productive ways. So that's what we had to say today. If you have questions or comments that you want to follow up online with, or after the presentation with, I guess Autumn is probably your main contact point. But at this point, what do? Do I hand it back to you, Liz? Can you take over?
So I've got one question from the audience.
Okay.
The question is, this is great information about accessible reading of math that's been published. Have you also worked on accessible math entry, and are there standards for that?
A little bit. We haven't done nearly as much of that as we would like to. That is something that people are strongly interested in, particularly because of the need for things that students can do for standardized testing and whatnot. There aren't any standards. I know of a couple of grant proposals that for research projects to try to work out better accessible authoring methodologies or enhance better accessibility in existing ones. ETS, the testing service in design science, actually has put in a grant proposal to work on making MathType more accessible as an authoring platform. But beyond that, I don't actually know of a whole lot. It's possible that Neil Seufer would know of more. He's, our accessibility researcher. And if it's a pressing need for you, I'd suggest you write to Autumn, and she can put you in contact with Neil afterwards, and perhaps he can, dig up the right contact in the accessibility community that might be working on that.
Great. Let's see, I've asked her whether that answers the question. We have a comment. I would point out that as a publisher who does not have XML workflow, design science MathType still forms the core of our workflow involving math from authoring to typesetting, distribution, and archiving. Sounds like a rave.
Thank you.
Okay, here's another question. Will support for MathML3 within HTML5 eliminate the need for MathJax?
Well, over time, I kind of hope it will. I see it as a transitional technology. It's not clear to me what the time frame would be. The way I kind of imagine this going is that, when you publish a completely standard HTML5 page and put a slug of JavaScript to load that MathJax script into it at the top, what happens today is in a whole lot of browsers, MathJax says, you know what, I have to do all the heavy lifting here. I pretty much have to, you know, translate this into CSS and HTML code and whatever. But even now, if you happen to be running in, you know, Netscape 4, Firefox 4, it basically can just pass that page through, and Firefox just displays it. And so the way we see this going is over time, more and more browsers, MathJax just becomes a transparent layer that passes things through, and you're programming straight to the browser. And it is only dealing with the long tail of non-compliant older browsers or fringe browsers that you may still have to deal with as a publisher. But at some point, you know, the logical conclusion is you look at those browser statistics and you know, 97.8% of your users are using an HTML5 compliant browser that'll just display the MathML, and then you can take that slug of JavaScript back out and your data's all still good.
Okay, I don't see any more questions. Anyone else have questions? Please type them into the question window. Let's see. So, and because I'm going to show that screen, Robert, because I usually have a helper, and we're not there right now. And I'll view full screen mode. Those are the upcoming events, and that